Thank you very much for that introduction. That was very flattering. I'm going to repeat that to my children this evening to explain to them why they should listen to me. My so let's see. Today I'll talk about two pieces of work that I was involved with. One of them is from 12 years ago, and one of them is from this year. But they're both on the theme of consistency of clustering, and the main reason I want to talk about them is because they're actually interesting open problems associated with them. And by the way, feel free to ask questions anytime. I have the chat window here, so if you type something in there, I'll definitely see it, or you could just ask out loud. So, clustering, you're given a bunch of points, you want to divide them into groups. So there are two rather different contexts in which this arises. One is in exploratory data analysis, where you actually want to find meaningful structure in data. So for example, a supermarket might want to understand its customers, and to try and do that, it could cluster them and hope that there are some coherent, distinct clusters. A very different type of application is vector quantization. There's basically some sort of enormous space, and what you want is a finite set of representatives for the space, where each point will just be associated with its closest representative. So in those kinds of applications, you don't care about any natural clusters or any meaningful structure or anything like that. The only thing you care about is the error induced by this discretization. So I'll talk about both types of clustering, but why don't we start with the first one, which is looking for meaningful structure. And so, for example, over here, we have a few points. What is the meaningful structure over here? How many clusters are there? And well, there could be 2 clusters, there could be 3 clusters. And one look at the picture and you can immediately tell that there is no right answer. And because this is a common situation, hierarchical clustering is really very attractive. It contains clusterings at all possible granularities, and it avoids answering these essentially unanswerable questions like how many clusters are there. And in fact, I think a common theme in unsupervised learning is that thinking hierarchically just makes a lot of annoying technical hurdles go away sometimes. So there are lots of hierarchical clustering algorithms out there. One of them, a very old algorithm, is single linkage. Okay, it's fairly well known. And actually, one of the interesting things about this algorithm is that it's used in both statistics and computer science, but for very different purposes. In statistics, it's a clustering algorithm. In computer science, it's the minimum spanning tree algorithm. Okay, but it's the same procedure. And so let's just quickly go through it. So you have a bunch of data points, and initially you think of each of them as being in a cluster by itself, a singleton cluster. And then you merge the 2 closest, and then the next 2 closest, and then the next 2 closest, and then you merge these 2, okay? And so at this point, you've got 3 non-singleton clusters and 3 singleton clusters, and then you keep going in this way, okay? And so you get a hierarchy, and now to get 2 clusters, you just cut the largest edge, and so on. So this is a nice, simple algorithm. It's been around a while. Is it any good at all? Okay, and how do we answer these questions? So one approach to sort of answering that question has been to try and formulate properties of, properties that any reasonable clustering should possess. And this was a project that was started in the 60s and 70s by people who work on taxonomy. And in 2001, John Kleinberg also took a crack at it and came up with a bunch of axioms or properties that clustering should possess. And according to his axioms, basically the only decent clustering algorithm was single linkage, okay? And since then, other people have also tried to do similar things, formulate maybe slightly different properties. And very often single linkage comes out on top. And this is kind of weird because in practice, this is not such a good algorithm. And so there's a real disconnect over here. And what could be the reason for that? So one possible reason is that these theoretical analyses, these axiomatic analyses, completely ignore the statistical aspect of the problem. And in fact, when you start to think of single linkage in a statistical way, then its flaws become much more apparent. Okay. So what I mean is that typically, or very often, the data you have are not just arbitrary points, but are random draws from some underlying distribution. And you have no idea what that distribution is, but the mere fact that the points are drawn from some distribution gives them some special properties, okay? In particular, one of the things that you'd hope is that if you were to run the clustering algorithm on a data set and then draw another data set of similar size from the same source, the result of clustering that second data set would be similar to what you got on the first data set, okay? And carrying that further, what that means is that as the number of points goes to infinity, the clustering you get should converge to something, okay, consistency. And hopefully should converge to something that's really meaningful and informative about this underlying distribution. So all this talk of consistency is just, obvious to anybody who is doing supervised learning or classification, because in that setting, there is a very well-developed theory of consistency based on BC dimension, Rademacher numbers, and so on. And the results are very satisfying. But when it comes to clustering or unsupervised learning, the picture is much, much different, and it's actually very primitive. There are almost no clustering algorithms for which consistency properties are understood, okay? And in that respect, actually, single linkage is not too bad because it turns out, and this has been known for a while, that it is trying to converge to something reasonable, okay? And so let me say what that is. Okay, so here is a picture of a density that has 4 modes. And so anybody who looks at it will immediately say, yeah, there are 4 clusters, okay? But where exactly should we draw these clusters? Should we draw them in the middle over here, this orange region, or maybe a little larger, the red region, or maybe a little larger, the purple region? Well, the good thing with hierarchical clustering is that you don't have to choose. You can just say all of those are clusters, okay? And so that's what we'll be doing. So what we'll say is that choose any density level lambda, and now look at the region of the space that has density greater than lambda, okay? Any connected component of that region is a cluster. And since there are infinitely many choices of lambda, this means that we have infinitely many clusters, okay? So this inner thing is a cluster, the slightly larger one is a cluster, the purple one's a cluster, and the same for all these 4 groups, okay? So there are infinitely many clusters, and they form a tree. And this is the cluster tree. And it turns out that this is what single linkage is trying to converge to. So let's just look at a slightly more specific example over here. So this is a density on 1 dimension. And once again, we can pick a few density levels. So we pick level lambda 1 over here. And if we cut off at that density level, we get a small cluster. We get this little interval down here. And so that is the single cluster at that level. If we look at density level lambda 2, we get 2 clusters. We get this interval over here and this other disjoint interval over here. There are 2 clusters at level lambda 2. At level lambda 3, we have this big cluster over here and this smaller cluster on the right, okay? And in this way, we get infinitely many clusters. And these clusters have the hierarchical nesting property. Any 2 clusters are either completely disjoint or one is nested within the other. And so they form an infinite tree, the cluster tree, okay? So it is this object that single linkage is trying to go for, Okay, and so let's look at how it is trying to do that. So let's say we have a finite data set like this. It starts by merging the two closest points. And you can think of that as sort of an approximation to this cluster over here. And then it merges in one more point, and you can think of that as an approximation to this cluster. And then it merges these two, and that's an approximation to this. And then it puts in one more, and that's an approximation to this. And then it merges these, and that's an approximation to this larger cluster over here, and so on. And so in this example, it really seems like, at least in some intuitive sense, single linkage really is consistent with the underlying cluster tree, okay? So in order to go further, we need a formal definition of consistency. And this is something that Hartigan came up with in the late 70s. And he had this very nice definition. So what he said is that look at any density level lambda and look at any two clusters at that level. In other words, look at any two connected components of that level set. Okay, so look at any two clusters. The property we want is that there should be some subtree that contains all the points in one cluster, and another subtree disjoint from the first that contains all the points in the second cluster. And in fact, we just need that to hold as n goes to infinity. Okay. So if we look at this example up here, let's pick a level set. Like, let's say we look at this one over here, this fourth line from the top. Okay. So we have this cluster on the left. That could be our A. What are the points that fall in A? Well, the points that fall in A are just 1, 2, and 3, and they are in some subtree. And the points that fall in A prime on the right are 5 and 6, and they're in another subtree. Okay, so certainly this picture seems to satisfy this property, and we don't need it to hold for a small data set. We just need it to hold in the limit. Okay. Now, it's not actually a coincidence that this example looks good. What Hartigan showed in 1975 is that actually single linkage is consistent in one dimension. And this has been one of the few really decent results in the statistical theory of clustering. Okay, so Hartigan showed that single linkage is consistent in one dimension. And so the natural question is, what happens when the dimension is more than one? And at that point, the story becomes, the news becomes a little bad, okay? A few years later, Hartigan showed by a reduction to continuum percolation that actually for any dimension more than one, you lose consistency. And the problem is, so if you, let's say you have two large clusters like these that are high density regions, okay? What we need is for the clusters themselves to get fully connected, to individually get fully connected before any sort of bridge is built between them. But in the single linkage procedure, if there is one point in A and another point in A prime, and these 2 points are very close together, then a bridge can be put between them before A becomes connected or before A prime becomes connected. And when the dimension is more than one, these kind of coincidences are basically inevitable, okay? And so that's the problem. So what we showed, what Kamalika Chaudhuri and I showed a dozen years ago, was that in fact, you can just change single linkage a tiny bit, and then it becomes consistent in any dimension. And moreover, not only do we have the asymptotic result, but you also get a finite sample rate of convergence. And you can show that in fact, those rates are close to optimal in a minimax sense. So, what is this tweak? How do you have to change single linkage to make it consistent? And in order to understand that, it's useful to think of single linkage in a rather different way in terms of near neighbor graphs. And so let me talk about that now. So near neighbor graphs, of course, are very popular in machine learning. They're a way of capturing the local structure of a data set. So you start with some data, maybe in very high dimension, and then you create a graph that has a node for each data point and where nearby points get joined by an edge. okay? And so you start with this large, unfathomable data set, and instead you get this nice, clean mathematical object that's easier to work with. And this graph then gets used for all sorts of things: clustering, semi-supervised learning, doing embeddings, regularizing, supervised learning, okay? So it's a very useful data structure. So how exactly do we build this graph? It turns out that there are two popular ways of doing it, okay? One way is to connect all points within a certain preset distance, say 0.1 or 1.1, something like that. And the other is to connect each point to its k nearest neighbors, okay? And the reason there are two ways of building graphs, or two popular ways of building graphs rather than just one, is that neither of them is really entirely satisfactory. And so usually it's a case of picking the lesser of the two evils, okay? So what's wrong with these? So let's look at the first one, okay? So when you connect points at a certain distance, this runs into trouble when there are clusters at multiple scales. So if you have a situation like this, well, if you pick R to be small, you will correctly join up all points in the small cluster and maybe in the medium cluster, but in this large cluster, you might get no edges, okay? But if you pick R large enough to deal with the large cluster, then it'll end up merging the two smaller ones. So no matter what value of R you pick, you're in trouble, okay? This kind of multi-scale structure is not pathological. It's really the norm, okay? And even in very simple data sets, for example, in something like MNIST, so in MNIST, the natural clusters are the zeros, the ones, the twos, and so on. And these clusters have very different sizes. The ones, for example, are a cluster of very small radius relative to something like the eights, which are much larger. So multi-scale structure is the norm. And in order to deal with such cases, the second technique is often suggested, where you just connect each point to its k nearest neighbors. And that would correctly deal with this example on the left, because in the small cluster, its k nearest neighbors would presumably be in the same cluster, assuming there are enough data points. And it would also do something sensible in the large cluster. But the problem that occurs now is that you get spurious connections. Okay, in many data sets, there are some points that are outliers or, just a little further out than the others. And connecting such points to their k nearest neighbors can wreak havoc with this graph and end up joining up regions that really should not be joined, okay? So the problem over here really is that we're trying to take multi-scale structure and just flatten it into a single graph. And that's just inherently problematic. So maybe we could just instead think hierarchically, and instead of choosing a single nearest neighbor graph, why not take a whole hierarchy of graphs at different scales? And this is implicitly what single linkage is doing, okay? So here's another way to think of single linkage. You can think of it as having a knob that it's gradually turning from 0 to infinity, okay? And when the knob reaches some value R, then we end up joining together all points at distance R or less. And we look at the resulting graph. We're going to call it G sub R. And we just spit out the connected components of that graph. We ignore singleton components. Okay, so we turn this knob. When we get to R, we join up everything at distance R, ignore singletons, and spit out the connected components, and we keep going. This is essentially what single linkage is doing, okay? Another way to state this is that any data point, xi, is initially inactive when the knob is at 0. And it becomes activated when the knob reaches the distance from xi to its nearest neighbor. At that point, xi becomes activated. And from then on, xi is always active, okay? So in order to make single linkage consistent, we just have to make two tiny changes to this, okay? And so I'll show you the changes. So this is single linkage, and this is the altered version. So we've just made two little changes over here, this and this, okay? So again, we keep turning the knob, but now a point becomes active, a point xi becomes active, the radius at which it becomes active is not the distance to its nearest neighbor, but the distance to its kth nearest neighbor. And this is basically a form of robustness. Okay, it makes the whole thing more robust. And the second thing is that when the knob is at R, we don't just join together points at distance R, but we also allow slightly larger distances. We're going to take alpha to be square root 2. So we join together points within distance R square root 2. And if you make those two changes, then it turns out that the single linkage procedure, this amended procedure, is consistent in any dimension. And moreover, you can also give finite sample rates. Okay. So we'll go through the argument in a few minutes, but I also wanted to talk about finite sample rates and what that would mean in this case. So we know that when you have a cluster and you let the number of points go to infinity, eventually you will detect that cluster, okay? But if there's a cluster that really stands out, that is very salient, then we would hope to detect it much earlier on, for just a small value of n, for just a small finite data set. And in order to argue that, we need a notion of cluster salience. What does it mean for a cluster to be particularly salient or to stand out? Okay. And it turns out that in order to define this, there are really just two effects that we need to capture. So the first effect is the following. It's shown by clusters that look like a dumbbell like this, okay? So this is a cluster that's a high density region, but it's got this really narrow, this really thin bridge in the middle. And as a result, in a small finite data set, if you just have a small finite data set, this would look like two disjoint regions. So to deal with this, we just introduced the notion of a buffer zone, where for any set Z, we let the buffer zone Z sub sigma be all points within distance sigma of Z. Okay, so it's the Minkowski sum of Z and just a little ball of radius sigma. So that's the buffer zone around a cluster or around a set. The next effect that we have to capture is the following. So these are, in both these pictures, there are two modes and two clusters. But on the left, the two clusters are separated by a region of significantly lower density, whereas on the right, they're separated by a region of density that's just slightly lower. So it seems like the case on the left would be much easier. And so we need to capture that. Okay. So just these two notions give us a definition of what it means for clusters, for regions of RD to be separated, okay? And so we say that two regions, so here are two regions, A and A prime, and these are just any old regions. They will in general be pretty weird looking, okay? So any two regions, we say they're sigma epsilon separated. If they're separated, so there's some set S such that any path from A to A prime has to go through S. And moreover, the density anywhere in S is substantially less, 1 minus epsilon of the density in A or the density in A prime. And this holds even if you look at the buffer zones of size sigma around each of these sets. Okay, so this is how we can define a notion of separation between, in this sort of non-parametric setting. And I guess one thing to point out over here is that for any A and A prime that are distinct clusters, there is going to be some sigma epsilon for which they're separated. Okay, it might be very small, but there'll be some positive sigma epsilon at which they're separated. Okay. So here is here's the sort of finite sample result then. So the following thing holds for the modified single linkage procedure. with high probability uniformly over all clusters A and A prime. Okay, so let's say that A and A prime are clusters at level lambda. Okay, so within A, the density level is greater than or equal to lambda, and likewise with A prime. And let's say that they are sigma epsilon separated. Okay, then when the number of data points exceeds this value, they will be distinguished by the hierarchical clustering. And one way to say it is the following, that when you're turning that knob, there will be some intermediate graph G sub R. When the knob hits the number R, there's going to be some R at which A is a connected region. Okay, so A lies within some connected component of G sub R. A prime lies within a different connected component of G sub R. Okay, so there's some setting at the knob at which A prime will be in one connected component and A will be in a separate connected component. And this is the value at which that occurs. And it turns out that this is going to be close to minimax optimal. Okay. So let me go into the argument for this. So one thing that we are very familiar with is Erdős-Renyi random graphs, where you have n nodes. And between any pair of nodes, you just flip a coin and you put an edge there with probability p. Okay, and the sort of questions that we're interested in is, as you increase p, what is the value at which you get a giant component, a component containing almost all of the nodes, or what is the point at which the graph becomes connected? In a statistical setting, the graphs that occur more often are random geometric graphs. So here, the points are chosen at random from an underlying density, and the graph is constructed by connecting points according to some criterion, like let's say distance less than r. So again, you get a random graph, but now the randomness is entirely in the nodes, whereas in an Erdős-Renyi random graph, the randomness is entirely in the edges. Nonetheless, the questions that we're interested in are much the same. What is the point at which you get connectivity? Okay, and so that's the sort of argument that we'll have to deal with in this setting. Okay, so here's the algorithm again. Okay, so this is the modified k-means algorithm. We turn this knob, and each point becomes activated when the knob hits the distance from the point to its k nearest neighbor. Okay, and then amongst all the activated points, we join up any 2 points whose distance, whose interpoint distance is the current knob setting r times square root 2. Okay. So the hope is that when we're on a small setting of the knob, since we're only getting points that are really close together, we're essentially just dealing with very high density regions. And as we gradually turn the knob more, we move to progressively lower density regions. Now, single linkage just uses k equals 1. Okay, so it just looks at the distance to the nearest neighbor. And so what it's hoping, for example, is that if you look at the 2 closest points, if you look at the 2 closest data points, that they lie in the region of highest density. That's what implicitly single linkage wants. Okay, that the 2 closest points correspond to the highest density region. And that might be true, but it could also be that just due to having a finite sample, the 2 closest points are somewhere else. And a single coincidence of this kind will completely derail single linkage. Okay. So we have tried to fix that by simply choosing a larger value of k. And so let me just briefly explain why that's enough. Okay. So what we know from VC bounds is that because the class of balls is not very complicated, it has VC dimension b plus 1, what you can expect is that every ball in space, even though there are infinitely many, will contain roughly the right number of points, okay? And so if you have n data points, and you have a ball B, let's say the probability mass of the ball is f of b, f is the underlying density. So then the expected number of points in the ball is n times f of b. And what the VC bounds tell us is that the actual number of points in the ball will actually be this plus or minus d log n, okay? Here I'm looking at bounds for the case where the expected number is some small constant, okay? So then the actual number will be that plus or minus d log n. So this is great. Every ball contains roughly the right number of points, plus or minus d log n. But what this suggests is that the value of k we should take is d log n, okay? And if we do that, then we don't really have to worry about the sampling, the kind of sampling error I was talking about, okay? And so that's the first thing we need to do. Okay, if we do this, it will indeed be the case that the points that get activated the first are indeed in the highest density regions, and the points that get activated later are lower density. So the next thing that we have to talk about is separation, okay? And so here's, okay, so what do we need to show? So let's say that there are two clusters, A and A prime, and let's say that they are sigma epsilon separated, okay? So we have to show that there's some point when we're turning the knob at which the graph we get, G sub R, has got one connected component containing A and a separate connected component containing A prime. And there are two parts to this. The first thing is just to show that everything in A is active and everything in A prime is active, and that the two regions are separated from one another. That turns out to be the easy part. The hard thing is showing that A is internally connected. That's the hard part. Okay, so let's start with the easy part first, just showing that A is actually separated from A prime. And with these large deviation bounds, it's not hard to show that as you're turning the knob, there's a particular value R, there's a particular setting of R at which every single point in A has got K other points within distance R and therefore is active. So all of A is active. And likewise, all of A prime is active, okay? At the same time, nothing in the separator set is active because nothing has got K points within distance R. Okay, so none of this is active. And moreover, this R is less than sigma over 2. Okay, and if this is the case, we have that all of A is active, all of A prime is active, and any path from A to A prime has to jump over the separator set. And the separator set is so wide that it's impossible to jump over it given the current radius. And so these two regions really are disconnected from each other. Okay. And so the separation is very easy to argue. The harder part is to show that A is internally connected at the same level, and likewise with A prime. And so I'll say a little bit about that. Okay, so here we have one of these clusters, A or A prime, and as usually, it is just some weird looking region. Every point in it is active, as are points in the little buffer zone around it. But now we have to show that between any two points, there is a path, okay? Because we're just connecting points that are at distance R square root 2 from each other. And so between any two points X and X prime, there's a path consisting of points that are distance R square root 2 of each other. Okay. Now, the worst case is when the cluster actually just looks like a thin tube. And we have X at one end and X prime at the other end. And somehow we have to find a path from X to X prime. And the cluster is so thin that essentially the path is going to have to use points in the buffer zone. Okay, so we're going to have to find some path in the buffer zone that goes between these two. This is why we ended up connecting points that are a little further than distance R from each other. We allow it to be R square root 2, okay? Because the larger we allow this to be, the easier it is for us to exhibit a path from x to x prime. And it turns out that if you set alpha equals 2, it's very easy to show connectivity. And we were able to do alpha equals square root 2. And it's an open question to bring it down to alpha equal 1. Okay, that would be ideal. So, so let's see how this goes. And so this will just be, so this is an argument about connectivity. So here are these 2 points, x and x prime. And they're within the same region A. And so there's a path in that region that connects the two. There's some path P. But we have to connect the two using data points, okay? So we want to find a sequence of data points that connect x to x prime, such that any pair of consecutive data points are just within distance r square root 2 of each other, okay? And the way we do that is that we say, well, we're just going to build this sequence one at a time. Let's say we're currently at xi. We've been moving along the path. We're currently at xi. We look at a ball of radius r around it. And this dot over here represents the furthest along the path that we can reach within distance r of xi. If this furthest point along the path is already x prime, then we're done. We're golden, okay? But let's say that we haven't quite got to x prime yet. We're somewhere along the way, okay? So now let's draw another ball that's now centered at this point and again has radius r. So now xi is on the outside of the ball. And let's look at the hemisphere defined by this normal, the normal between the center of the ball and xi. Okay, so we look at this hemisphere. By VC bounds, there's at least one other point in the ball. And that's going to, at least one other data point in the ball. Since it's very close to A, the data point is also active. And its distance from xi is at most r square root 2. And moreover, it's further along the path in the sense that if we look at distance r from it, we'll get somewhere further, somewhere out here, okay? And so in this way, we construct a path. And the open question here is to see whether it's possible to do this more economically. Anyway, so that's how one shows the finite sample rates. And that implies consistency because any pair of clusters is sigma epsilon separated for some positive sigma and epsilon. And so once you have the finite sample rate, you automatically get consistency, okay? The lower bound is shown using Fano's inequality, which is quite customary in these settings. Okay, so this paper was published a dozen years ago, and since then there has been some other work on a particular aspect of this problem, and that has been revisiting Hartigan's notion of consistency. So if you recall what Hartigan said, the way Hartigan defined consistency is that if you have two clusters, then for large enough n, there's going to be some subtree that contains all the points of one cluster and a disjoint subtree that contains all the points of the other cluster, okay? And this is great. It's just saying that distinct clusters will eventually be separated in the tree, okay? Which is perfectly sensible. But what this doesn't guard against is clusters becoming fragmented, okay? And I'll show you what is meant by that. So over here is a density where there should be two clusters. There are two modes. And what we'd like is to get a tree like this one on the right. But Hartigan's definition makes it possible to get a tree like this, where the cluster on the left, there is some sort of fragmentation over there, okay? And so what more recent work has done has been to propose alternative notions of consistency that disallow fragmentation, okay? It's been to say that, look, Hartigan's notion is not complete. We need to round it out to also prevent fragmentation. And it turns out that this same algorithm, the one that I just talked about, also takes care of this other problem. So in terms of open problems, I think the nicest open problem over here is the following. So what we've seen is that there is this very natural notion of a limiting object for hierarchical clustering, which is the cluster tree, and that modified single linkage actually converges to it. But what would be really wonderful is to find other natural limiting objects for hierarchical clustering, and to find procedures that converge to these. And in particular, those of you who might be familiar with things like graph Laplacians, heat kernels, and so forth and so on, it would be very interesting to see if some sort of limiting tree could be fashioned out of those as another compelling limit for hierarchical clustering. Okay, so that's what I was going to say about hierarchies. I also wanted to talk briefly about k-means. And since I think there's a very interesting open problem over here. And so I was mentioning these two types of, these two distinct uses of clustering, finding structure in data versus vector quantization. And k-means is basically the canonical vector quantization cost function. If you were to write down a cost function for vector quantization, it would be k-means. Okay. It's also probably the most popular clustering algorithm. So what is known in terms of the consistency of k-means? What happens as the number of points approaches infinity? So unfortunately, not very much is known. Okay, so let me just briefly describe the what's out there. Okay, so as before, let's say that there's some underlying distribution in RD from which data points are drawn, IID. Okay, and we have n data points. And so what k-means does is to find the best set of k-centers, the set of k-centers C sub n, that minimize the k-means cost function, the distance from each point to its nearest center, add them up, take the average, okay? But similarly, we can talk about the best k-means solution for the underlying distribution, okay? And so the set of k-centers C prime that minimizes the expected distance of when you draw a point from the underlying distribution, the expected distance from that point to its nearest center. And let's call that C star. So what is the relationship between these two? And what Pollard showed in 1981 is that if this distribution has finite second moment, and if this set of k-centers, C star, is unique, then the solution to k-means converges almost surely to, as n goes to infinity, to the solution for the underlying distribution. Okay. And so this sounds like a nice result, but the problem is that C sub n is not something we can actually produce because it is the solution to an NP-hard problem. So, so this convergence result is not really something algorithmic. It says, if we were allowed, if we were somehow given the ability to produce C sub n, then we would converge to C star. Otherwise, we have no idea what happens, okay? And so what would be nice is to actually look at a specific k-means algorithm and to look at what that converges to, what the output of the algorithm converges to. So one k-means algorithm that I am very intrigued by is the sequential k-means algorithm. And this is something that has been proposed many times in the neuroscience literature, in fact, many variants of it, okay? It's a nice online k-means algorithm, and it's very simple. So what happens is that you get a stream of data forever, okay? In our case, we can pretend that the data are drawn from this underlying distribution, and you initialize the centers to the first k data points in that stream, okay? and you set the counts for the centers to be 1. And now you keep going for t equals k plus 1, k plus 2, ad infinitum. You get the next data point, you find the closest center to it, and then you update that center to just average in the data point. That's it, okay? So it's a very simple algorithm. You get the next point and you just average it in to the closest center. And the question is, can we say anything at all about this, okay? In the situation where the points x are drawn from some underlying distribution, does this process converge to something at all meaningful? What does this do, okay? And so this has been something that, there has been a lot of experimental work on this procedure, and I'd be happy to tell you what kind of results have been obtained. But in terms of theoretical guarantees, really not much has been known. And so I can tell you one result that we recently obtained. So here's another way of writing down the update. When you see a new point x sub t, you look at its closest center, w sub j, and you average it in. And this is another way of writing the average, okay? It turns out that in analyzing this, a big difficulty is that there can be some clusters that very rarely get updated. A cluster that really just contains a few points, and it very infrequently gets updated. And so what happens is that the counts for that cluster remain very small, while the rest of the world is moving on, and everything else, is changing much more frequently. And this creates a lot of problems in the analysis. So to handle that, we proposed a modified procedure where the update is similar, but now, instead of looking at the total number of times that center has ever been updated, you just look at how much it was updated in the last square root t time units. Okay, so when you're at time t, you just look at how much it was updated recently. And so there's a modified learning rate. And under this condition, one can show that the centers you get do converge almost surely to the set of stationary points of F. Okay, and I won't go through the argument. It's quite it's a little bit of a departure from a traditional sort of stochastic gradient descent analysis because basically because each center has its own learning rate, which is this value that I've highlighted over here. Okay. But the open problem over here is what else can we say about what this algorithm is converging to? Is this it? Can we say something about its solution being good in some other sense? Okay, and it's such a simple procedure. So there should be some clean answers for it one way or another. Based on experiments, one thing that is observed is that if you compare the solution of this algorithm to, say, standard k-means Lloyd's algorithm, the solution is much, much worse. Okay. However, if you give it extra centers, okay, so instead, if you give it, let's say, not k centers, but you allow it maybe k squared or 10k, I don't know what the formula is, okay, if you give it a whole bunch of extra centers and you then compare that solution to the best k, to the Lloyd's k-means solution, then it's pretty good, okay? And so it would be really interesting to have some analysis that would kind of back up those kinds of findings. Okay, so that's all I was going to say, and I'd like to thank my co-authors, Kamalika Chaudhuri, Samori Potufe, Ule von Luxburg, Gaurav Mahajan, and Geelon So.